In this video, we're going to talk about linear programming, which is the process of taking some inequalities and graphing them together and finding a point that maximizes or minimizes an objective function. And we call these inequalities that we're going to graph, we call these the constraints, and the overlapping region is called the feasible region. And we get to a pretty interesting result if we have, for example, a real quick sketch here. If we take some inequality, maybe we're going to graph a line, and we have some shading for that. Maybe we're going to shade this way. And then we have another graph, and it might look something like this. And maybe we're going to shade this way for this one. And we say that all of them are positive. Well, we get our double shaded region ends up being right in the middle here. Okay, so we find our double shaded region, and we're familiar with how to do that with inequalities. And this double shaded region here has some vertices. And these points are the points that we're going to look at. And these are called the vertex points. These vertex points are where we'll find the maximum or minimum for our objective function. So let's see how this works with some examples. So for an example here we have a system of inequalities. And the instructions for us is we want to find the maximum and the minimum for an objective function with these constraints. Alright, so these constraints are just another word for limitations, we could say. And so here we have our given limitations right here. This is our system of inequalities. And so we're going to graph these. Alright, our first one we have is 2x plus 4y is less than or equal to 20. To graph an inequality, we've got to find the boundary line first. So we're going to graph the boundary line. 2x plus 4y equals 20. And so to do this, we're going to find our intercepts. If x is 0, then we're just going to have 4y equals 20, so y is going to be equal to 5. And so let's graph this, go by ones here. 1, 2, 3, 4, 5. We get a graph about a point here. And when y is 0, x is 10. So we can find that point out here. And now we're going to go ahead and graph our line. And we should use a straight edge for this, but we'll see if I can draw this. Okay. It is a solid line because it's or equal to. And because we have these two inequalities here, x is greater than 0 and y is greater than 0, that means that we're only looking at points in the first quadrant. So I'm just going to stop my line right there. And we'll shade here. So we'll shade below for this one. Okay. How do we know we shade below? Well, test a point. Let's test a point 0, 0 into this inequality. So 0, 0 is not on the line. Test it under the inequality. 2 times 0 plus 4 times 0. Is that less than 20? Yes, it is. All right. Next one. I'm going to graph our, let's graph x plus 3y is less than or equal to 12. Okay. And once again, we're going to graph the equation first. X plus 3y equals 12. And this one we might want to go ahead and put in slope-intercept form. Subtract the x from both sides. We're going to get 3y equals negative x plus 12. And divide by 3. Negative 1/3 x plus 4. Alright. So we have a y-intercept of 4 in this case. 1, 2, 3, 4. And a slope of negative 1/3. Okay. And that's going to be our intercept right there. And we'll graph the line. Let's try that again. point. And we're going to shade, let's test a point. First of all, test a point not on that green line, 0, 0. 0 plus 3y, is that less than 12? It sure is. So, we're going to shade below. Okay. Once again, we have x is greater than 0 and y is greater than 0. So we're going to limit the shading to the first quadrant because that's our other functions that we need to consider. So let's go ahead and we see our double shaded region. Actually, it would be quadruple because we have 4 others there. And so that gives us this area right in here. Okay. All right, and the key is we need to find the vertices. So this is called our feasible region that we're shading right into here. All right. We need to find the vertices of that region. Well, we have this guy right here. And that point right there is 0, 4. Okay. So we have 0, 4. That's one vertex. Then we have over here on the red line, it intersected at 10. And so we have 10, 0. That's another vertex. We have the origin, 0, 0. And then we have this point right here, where the green and the red line cross. Well, how do we find that point? We could guess there by our graph, and we might get our point. But to be more exact, let's take this system of equations and solve the system. So we have 2x plus 4y equals 20. And we have x plus 3y equals 12. And so let's use elimination here. So that's our system. Let's leave the first equation alone. And let's double the second equation. Double everything here. So let's take this whole second equation and double it. So 2x plus 6y equals 24. And then we can subtract. That gives us negative 2y equals negative 4. So y equals 2. And if we substitute that back into one of our equations, let's use the second equation. X plus 3 times 2 equals 12. And so we have 6. And subtract 6 from both sides. We're going to get x equals 6. All right, so we found our intersection point there. The point is 6, 2, which we kind of assumed from our graph. But we really should check it out. Solve the system to be exact. So our point here is 6, 2. So now what we need to do is we need to test each of these points. 0, 0. And 0, 4. And 6, 2. And 10, 0. Okay. And we're going to test the value of f, our function for each. So now we take our objective function, which is f equals 4x minus 3y. We now have some x and y values. We're going to plug it in and find f. Okay. So we have f equals 4 times 0 minus 3 times 0, which is 0. We have f equals 4 times 0 minus 3 times 4, which is negative 12. For 6, 2, we get f equals 4 times 6 minus 3 times 2, which is 24 minus 6, which is 18. And then we get f equals 4 times 10 minus 3 times 0, which gives us 40. And so we end up with a maximum and a minimum. So here is our minimum value. So 0, 0 gives us a minimum. And then we get a maximum at 10, 0. Okay? And in different applications, we want to maximize or minimize these things. So again, the process: graph the inequalities, find the 4 or 5 or more vertices, and then test each of those vertices into the function to find the maximum or the minimum, whichever you're looking for. And one more application, maybe a little more real life here. Let's say we have a manufacturer that wants to maximize the profit of 2 products. So we're selling 2 things. And he's provided you with some information. You know that product A gives him a profit of $2.25 per unit. Product B gives him $2 per unit. Okay, and then we have some other information. We know that demand information requires the total number of units produced to be no more than 3,000 units. So that's the most we can sell. And we also know the number of units of product B must be greater than, so we got product B must be greater than or equal to the half the number of units of product A. Okay? So we need to translate these into some inequalities. Okay? So let's start with, well, here's our constraints, first of all. Let's start with those. And so our first constraint, let's call that constraint number 1. We know that we have at most 3,000 units. All right, so first let's get some variables. Let's call A the number of product A, the number of units we sell. Okay, and let's call little b the number of product B. All right. Okay. And so we have, by constraint number 1, we know that A plus B must be less than or equal to 3,000. Maybe A and B are 2 types of coffees that we're making. Maybe we're making lattes and mochas at our coffee shop. And we only have 3,000 cups, so we are limited, and A plus B is 3,000. Then we have some other constraints, and let's say we know that product B must be greater than or equal to half of the number of units of product A. So we have B is greater than or equal to half of A. All right. So our last thing here is our function that we want to maximize here. Our objective function is this. We want to maximize our profit. So our objective function is going to be our profit function. Profit, well, we get 225 for every A item, so 225 times A. We get $2 for every B item, and so we're going to add those together. And that's our objective function there. Now let's go ahead and graph these and see what we can figure out. So we've set up a little graph here, and let's see what we can come up with. We've got our constraints. A plus B is less than or equal to 3,000. So let's graph the line. A plus B equals 3,000. We have intercepts of 3,000, 0. So when A, well, let's call this horizontal axis our A axis, vertical axis our B axis. So when A is 3,000, B is 0. So we have a point there at 3,000. So let's go ahead and graph that. Okay. And then when A is 0, B is 3,000. That's another point up here. Okay, and so we can graph that line like that. It's going to be solid because it's or equals to. And we're going to shade below. Okay. Now we have two other constraints that we kind of assume here. And that would be these constraints that A and B are positive. So let's go ahead and write that down. A is greater than or equal to 0. B is greater than or equal to 0. We're not going to be selling negative products. All right. So then we have that A is greater than or equal to 1/2 B. Actually, we need to fix this. I copied this down wrong. It is B is greater than or equal to 1/2 of A. All right. So we have this line B equals 1/2 A. Since B is like our Y value, A is like our X value, this is going to be a line with a slope of 1/2, and a y-intercept of 0. It's going to look like this. Okay, let's make that a different color. So let's go green. All right, so we get a line like that, and we're going to shade. Let's test a point. If we test a point like 0, 1,000, when A is 0, B is 1,000. Is 1,000 greater than 1/2 times 0? It sure is. So we're going to shade above. Okay. And our double shaded region is right here in the middle. So we're going to go ahead and erase this stuff here. Our double shaded region ends up in the middle here. All right, so we have our feasible region. Remember, that's called the feasible region. We need to find our vertices. We have vertices of that region are 0, 0. We have 0, 3,000. And we have this point right out here, which we can approximate, but let's go ahead and solve it. So let's take our system. A plus B equals 3,000. And we have B equals 1/2 A. Let's substitute A, and we're going to put 1/2 A in for B. 1/2 A equals 3,000. And so adding, we get 3/2 A equals 3,000. And let's multiply both sides by 2/3. All right, and that gives us A equals 2,000. Okay, plugging that back into our equation here, B equals 1/2 times 2,000, which is 1,000. All right, so we found this point here to be 2,000, 1,000. Now this shows why you need to use a straight edge when you graph. On this program I don't have a straight edge, but use a straight edge and it should intersect a little better. My lines are a little off there, but solving the system there shows us exactly. All right, so we got 3 points to test. Let's go ahead and test that, and then we'll be done. So we're going to test those into our objective function. So we have these here, 0, 0. We have 0, 3,000. And we have 2,000, 1,000. All right, so we test that into our profit function. And so our profit, if we sell anything or we don't sell anything, that's not a good deal. So that's just going to give us 0. Equals $0. Now if we sell 3,000 of the B items, we have 2.25 times 0 plus 2 times 3,000, and that is going to be $6,000. And if we test our third point of 2,000, and 1,000. That's going to give us a total of, this comes out to be 4,500 plus 2,000. So the whole grand total is going to give us 6,500. And there's our maximum profit according to this constraints that we have and our profit function that's given to us. And that's how we solve a system of inequalities and use linear programming to maximize or minimize an objective function.